Welcome. In this video, I will teach you how to solve any complex equation. Now, what do I mean by a complex equation? I mean equations of the following form. So we are going to have some z. This might be to the second power, to the third, to the fourth. This might be the modulus of z. We might have z times z conjugate. There's a whole lot of possibilities. We might be dividing by something of z. But the point is, we will have an equation involving z. This will be, of course, equal to something that could also involve z. Maybe this has something like 2 plus 3i times modulus of z, for example. I'm just making this up right now. But we have something like this. And the objective of the question is going to be determine the value of z. Okay, so that is the form of equations that we will analyze in this video. And I will show you that there is just a unique procedure that you can use and you will solve any equation like this, okay? And what is this procedure? Just go straight into it. Now, this goes like this. Step number 1, we want to define z equal to a plus bi. You can also take x plus yi, z equals x plus yi, if you like that better. It doesn't matter. But first, we have to define z equal to a plus bi. Why? Because as we will see, we want to determine this z, and this z has two components. It's not like when we solved for x, where x was just one number. In z, there are two components. So we have to write them explicitly. Now, what is step number 2? Now, well, we have to just put this into our equation. So just replace z for the value that we just wrote for z. That is step number 2, and this is always true. And now comes some algebra. We're going to have to apply some algebra. My mouse isn't working for some reason, so just algebra, with the objective of separating real and imaginary parts. So separate real from imaginary. I will give you some examples, so do not worry. And last step is solve the system of equations. Solve system of equations. So we will reduce a relatively hard problem in which we have two equations in one by splitting this one equation into two. That will now be easier. Okay, so that is the basis. Step 1, we have to replace z equal x plus yi. Sometimes you can apply some properties of the z, as we saw in the previous video. It's not really, you don't really have to do it normally. You can just replace right away. It might make it a bit harder, but it should be doable. And then we have to apply algebra and solve the system of equations. So let's go straight into some examples. So example number 1 is what we have right here. So modulus of z squared plus z is equal to 3 minus I. And we want to find the z for which this equation holds true. Okay, so what do we do? Step number 1, we say, okay, let's take z equal to, let's say, x plus yi. Okay, let's just call it like that. And now let's replace it in here. So we'll have the modulus of x plus yi squared plus x plus yi. And this has to be equal to 3 minus I. All right. Step number 2, replacing, is now done as well. And now begins the algebra with the objective of separating real and imaginary parts. So let's first of all do this part right here. So this is modulus squared. We know that this is now the real part squared, so x squared, plus the imaginary part squared, y squared. Please do not include the I in this square, okay? Otherwise you will get a minus sign and it will all be wrong. That's a very, 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 very common mistake. So please be very careful about that. And well, everything else stays the same. So x plus yi equal to 3 minus I. Okay, let's change colors now. And now we can already separate real from imaginary. And the way to do that is to notice in this equation, what is real? Well, everything without an I is real, and everything without everything with an I, sorry, is imaginary. I'm not sure I said that correctly. So without I real, with I imaginary. And if you have x plus yi, something that doesn't have an I, you cannot ever combine it with something that has an I by addition. So if in this equation we have a bunch of things that are real and a bunch of things that are imaginary, you can't put them together. It's not like 2 plus 3 is 5. You can't do that. 2 plus 3i is not 5 and it's not 5i. You cannot combine them. That's why we say they are linearly independent, but if you don't know what that means, do not worry. It's just to throw it out there. So what here does not have an I? Well, x squared plus y squared, x, all of these things on the left hand side do not have an I, and to the right hand side only the 3 does not have an I. So in order for this entire equation to hold true, then we need x squared plus y squared plus x, which is everything that is real on the left hand side, to be equal to everything that is real on the right hand side. So this has to be equal to 3. And this is the first of our two equations that we will get. And also the imaginary parts have to be the same. So y will be the imaginary part right here. So minus 1. When we do this procedure, do not include the i's. Well, they would cancel out later, but it's better to not include them, okay? So now we went from this equation right here, which was quite difficult, quite ugly, into these two equations right here. So we have now a 2x2 system of equations, which we know how to solve. So this will bring us to the last step, right? So solve this system of equations. Now, thankfully, the value for y is already ready. You can see y is equal to minus 1. So we can just plug it into the first equation right away. So we get that x squared plus x plus 1, this will have to be equal to 3. All right. So what comes next? Now, well, let's just simplify this further. X squared plus x minus 2 is equal to 0. Okay, so now we want to find the values of x. Here you can use your preferred method. If you can see, you know, just by looking at this, what the solutions of x should be, then you can factor this. If not, then I would recommend just going ahead and using the quadratic formula, because it's better to be safe than sorry, and it's only going to take you a minute maximum. So I'm going to do that. I always like to do this. I don't like to use many tricks because I know that many students don't really think about these tricks, and it can be a bit hard to factor kind of by eye and intuition. So let's just go ahead and use the formula. So what does the quadratic formula tell us? It tells us that x is going to be, well, minus b. What is b here? It is 1. So we get minus 1 plus or minus the square root of b squared, which is going to be 1, minus 4 times whatever goes with the x squared and this c. But there's already a minus sign here, so we get plus, and an 8 here, because 4 times 2. And all of this divided by 2a, but a is 1. So this is simply minus 1 plus or minus square root of 9, which is 3, divided by 2. So now we get two possibilities. Minus 1 plus 3, which is 2 divided by 2, so 1, or minus 1 minus 3, which is minus 4 divided by 2, it's minus 2. So our two possibilities are x1 equal 1 and x2 equal minus 2. Okay, so let's now put everything together. What does this mean? This means that our solution, which, remember, please, we're looking for a z of the form x plus iy. We already know that y is minus 1. So now we have two possibilities. z1, this is equal to 1 minus I, sorry. And z2 is going to be minus 2 minus I. Okay, so these are our solutions. And if you want to make sure that this is correct, you can just go back and plug them into this equation, and it should hold true. Okay, so this is example number 1. Let's now move to example number 2. Now this is going to be exactly the same procedure, right? This is just examples over and over again. So let's do the same. Step number 1, z is equal to x plus ib. If you want, well, x plus iy, I kind of combined the notations. You can call it a plus ib, or u plus iv, whatever you want. It doesn't matter, it makes no difference. Okay, now let's plug everything in here. So we get 1 minus, what is z? It's x minus iy. Okay, be very careful. This minus right here will make both parts negative. It's very common in this topic, right, in algebra of complex numbers, to make mistakes with the negative sign, so please be careful. Now we have this product here, so we have to take an extra step. Before replacing, let's simplify a little bit. So this will be by multiplying z bar, z conjugate, minus z bar, z. Now here there are two possibilities. You can either just go ahead and replace without thinking too much about it, or if you know some of the properties, this might just save you some work. Now let's say you don't know the properties or you forgot about them. Well, z conjugate, this is something you have to know, so this is just, we are just going to replace it. This is going to be x minus iy. But what about this part right here? This is x minus iy times x plus iy. So if you don't remember the property that concerns this product, you just write it like this and you multiply. But if you do remember it, then you will know that z times z bar, or the other way around, they commute, so it's okay. This is simply the modulus of z squared. So if you know this, then you just write modulus of z squared, and now you write the form of that. And as we already know, this is simply x squared plus y squared. Okay, so knowing the properties helps make things faster, but it's not necessary in this sort of problem. There are other problems of other kinds where it is actually very important. Okay, and this has to be equal to minus 2 plus 2i. Now we have done the step of replacing. Now we have to separate the real and imaginary parts of these equations. Okay, so well, first we can simplify a little bit. We can see that we have a minus x right here and a plus x right here. So this will cancel this. Anything else that cancels out? This, no. Okay, that's fine. Okay, so now real part. I want to put re and 2 points. So we have 1, that's real. Then we have minus x squared minus y squared. That's also real. And this is going to be equal to now the right hand side, so only minus 2 is real on the right hand side. Perfect. Now the imaginary part. So we have minus y, then we have another minus y, so let's just add a 2 in front. That does not look good, let me fix that. So we have minus 2y, and that's actually it, there's nothing more on this side, and this has to be equal to 2i. Okay, so now we have to solve this system of equations. We can see that, once again, the imaginary part is much easier to solve. This isn't always like this, it really depends on what the problem is. It just happened to be the case in these two examples. So we can see that y, oh, whoops, I made a big mistake here. We're not supposed to write the I here. I hope you noticed that. Do not write the I, especially, you can write both I's, so I's at both sides so that they cancel out, but only writing it in one place is a big mistake, because if you do that, you're going to end up with y is equal to something times I. And then when you put it into your z equal x plus iy, you're going to get I squared, which will cancel out, and you are going to end up with a real number when you should have a complex number. So please don't make that mistake. Okay, so in order for this to hold, y has to once again be minus 1. Great. Now with that knowledge, we can put it into the real equation. So the real equation will then be 1 minus x squared minus 1 is equal to minus 2. Okay, so here we can simplify a little bit, and this one will cancel out this minus 1, and we can multiply all by minus, so we get that x squared is going to be 2, or that x is going to be plus or minus the square root of 2. So we once again have two possibilities, of course. Let's now write them down. So z1 is going to be the, well, it doesn't matter, let's say positive square root of 2 plus, what was I think it was minus 1, right? Oh, so it's minus 1i, or simply I. And z2 is going to be minus the square root of 2 minus I. Let me make sure I remember the number correctly. Minus 1, and yes. Okay, so that's the solution here. So once again, if you want to check, just make sure to plug that into the equation. Now let us go for one final example. This is a little bit different, and I want to include this because I want to show you that teachers can get creative, but the underlying principle is the same. So if you identify that this problem is of this form, you can still just apply the procedure that I will show you here. So this problem states, determine the values of a such that z equals a plus 3i is a solution of this equation right here. So 4z times z plus 6 equal to 4z minus 61. I don't know why I keep going between z and z, so I really apologize about that. I can't help it, I'm not gonna lie. Okay, so what do we do here? Well, this is actually much easier than the previous cases, because before we had to start with z equal, well, we're already using an a, so I'm going to write it as a plus bi, and we had two unknowns, a and b, but in this case they are telling us to use z equal a plus 3i. So basically we only have one unknown here. We have to do just half the work. Well, not quite, but you know what I mean. Okay, so let's do exactly the same thing here. So we now have step number 1, our z. Step number 2, replace it. So we get 4 times this. So we get 4 times a plus 3i times a plus 3i, and this is plus 6. And this is equal to 4 times a plus 3i minus 61. Okay, so there's going to be a lot of algebra here, because now comes step 3, which is to separate real and imaginary parts. Okay, and well, we have to now just take a look at this. So what do we get? We have to, well, let's multiply the parentheses out first. So let's put the 4 in front. So we get a squared plus 3ai plus 6a. In this sort of problem, yes, it's annoying. Nobody likes having to do too much algebra, but make sure you do every step. Just take your time, take a breather, put on some music, and just multiply every single thing, okay? Make sure that you don't make a dumb mistake and you don't have to do this again, okay? So now comes plus 3i, so plus 3ai. Then comes this times this, so we're going to get minus 9, and then we have plus 18i. Okay, I think I did 1, 2, 3, 1, 2, 3, so 6. Okay, can we simplify something? We have 2 times 3ai, so we can just write this as 6ai. Anything else? I'm afraid not. Okay, and on the right hand side we get 4a plus 12i minus 61. And now of course we can multiply all of this by 4, so let's do that quickly. So we get 4a squared plus 6ai plus, oh damn it, I didn't multiply, whoopsie. It's not 6ai, it's 24 plus 24ai plus 24a minus 4 times 9, which is 36, plus 4 times 18, that's 40, and 4 times 8 is 32, so it's going to be 72i. I hope I did that correctly. 4a plus 12i minus 61. Okay, what can we simplify here? Well, we have 12i here and 72i, so that's going to simplify to 60i. Then we have 4a here and 24a here, so that's going to be 20a. And then we have 61 and minus 36. So let's add this here. So minus 61 plus 36 is going to be minus 31, and then still plus 6, so minus 25, I think. Minus 25i. Wait, there was no I. Whoops, almost messed that up. Okay. And now we have to separate real and imaginary parts. So let me just copy this and go to a new page, because I'm kind of running low on space here. Okay, perfect. So let's now separate this. So the real part, maybe let's change colors. This is going to be 4a squared plus 20a. This has to be equal to minus 25. And the imaginary part says that 24a plus 60 has to be equal to 0. So the imaginary part seems to be a lot easier to solve, and remember that both of these should be true. So we can actually choose to solve whichever one is the easiest, which is going to be the imaginary part. So a is going to be minus 60 divided by 24. Right? This just comes from the second part. And now we already, well, we can simplify this, to be honest, so maybe let's do that. So that's minus 30 divided by 12, and we can divide by 6, so this is minus 5 divided by 2. Okay, so this is actually a solution, so, you know, this is done. What was the other number? I think this was minus 5 divided by 2 plus 3i, I think? Yes, plus 3i. So this is your solution. And as you can see, it was the same procedure that we did before, but it was a little bit different. And you can check that if you had used this equation right here, you would have gotten to the same value for a. It just would have been, you know, much more work. Okay, so that is it for this video. In the next video, we will hopefully begin taking a look at the polar form of the complex numbers, and then slowly begin discussing the inequalities and some domains in the complex plane. So I will see you then.